Okay, what's going on here? Okay, looks like everything is straight. All right, so we're going to start with chapter 14 today. And in chapter 14, we'll be dealing with solids and liquids. And as you're going to see in the case of solids and liquids, their behavior, especially at the microscopic level, at the level of particles, molecules, atoms, is different, markedly different compared to the behavior of gases. I can mention one big difference between solids and liquids as opposed to gases, and that is that gases are very easily compressible, relatively speaking. I mean, you can easily reduce the volume of a gas by, let's say, half, by making variations in pressure and all of that. And that is certainly not true for solids and liquids. Solids and liquids are not very compressible. And that's just one difference. And we can understand the differences based on what happens at the microscopic level, as I said before. Okay, so we're going to talk about liquids firstly. What is a liquid? Well, a liquid is a substance, or a state, I should say, which has some properties in between the extremes of gases and solids. And this should be solids right here, not liquids. So please make a note of that. All right, so these are the properties associated with liquids. One, the particles of the liquid are close to each other, all right? It's incompressible, as I said before, and they have a definite volume, and they take the shape of the container that they're in, all right? So those are the main properties of liquids. And let me just say, with respect to the first property listed here, the particles are close together, but that doesn't mean that the particles are not moving. In fact, the motion of the particles is more like the particles sliding over each other, all right? So that's one difference between a liquid and a gas, because in the case of a gas, the particles are more independent of each other, and they will come into contact with each other, but not always or not very regularly, as opposed to liquids where the particles are always in contact with each other. But the particles are still moving because they're sliding over each other. Okay, now let's talk about this process called evaporation. Another term for evaporation is vaporization. And this is when you have molecules of the liquid escape from the liquid state to the gaseous or vapor state, all right? So basically we can represent that process by this simple equation here, where the liquid is converted to vapor, right? So that is evaporation or vaporization. And what happens when you have molecules escaping? It's usually, or not usually, it's always the molecules of a higher kinetic energy, higher than average kinetic energy that will escape from a liquid. So when those molecules escape, then the remaining liquid would have molecules with lower kinetic energy, and therefore, as a result, the liquid will be cooler compared to what it was before the higher kinetic energy molecules escape. All right, so that's basically why when you have a liquid evaporating, it basically exhibits a cooling effect on anything it is in contact with, all right? So this is basically what happens, for example, in the case of water. The molecules of water basically will start escaping the liquid state and move into the gaseous state, all right? And those are the higher average kinetic energy molecules. Now, another process I want to talk about here is sublimation. And sublimation is said to occur when you have a solid converted directly to a gas without going through the liquid state. So it can be represented by this equation right here. And a good example of this is iodine in the solid state. If you leave iodine in, let's say, a bottle at room temperature, then eventually you're going to see that the solid will be converted to the gas. So that is basically what sublimation is, the direct conversion of a solid to the gaseous state. Another one that you may be familiar with, another example you may be familiar with, is that of dry ice. And you may know that dry ice is basically frozen carbon dioxide. So if I took a piece of dry ice, which is CO2 solid, and I basically put it on a table at room temperature, then eventually what will happen is that the dry ice, the piece of dry ice will shrink and you're going to see fumes emanating from the solid, which would be the carbon dioxide in the gaseous state, right? So this is another example of sublimation where the solid carbon dioxide is converted to gaseous carbon dioxide directly without going through the liquid state. Okay, so that's sublimation. So now we're going to get to the concept of vapor pressure. So what is vapor pressure? Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. So what we're talking about here is a situation where if you have a liquid in a container like a beaker or a test tube, then just above the surface of the liquid, you're going to have vapor of that liquid present. Now, as we're going to see shortly, if the system is a closed system, then eventually you're going to have the conversion of the liquid to the vapor and the other way around. Let me go back to my pointer here. So that's what's happening, or that's what's being shown here. The liquid is converted to the vapor, and that's evaporation, but you can also have the vapor converted to the liquid, and that's condensation. So the reverse of evaporation is condensation. And in a closed system, you have this back and forth taking place. So we call that a state of dynamic equilibrium, where you have both processes, the forward and reverse processes, occurring at the same rate. So when that happens, the vapor that is present will have some amount of pressure associated with it because it's, after all, a gas, all right? So as stated here, in a closed system, after the liquid evaporates, some of the vapor molecule will go back to the surface of the container, will strike the surface of the container and go back to the liquid by condensation. So as I said before, you have this back and forth occurring, and the pressure exerted at that point is called the vapor pressure. So just to illustrate what we're talking about here, if you have a beaker of a liquid, and that liquid could be anything, like water or ethanol, if you leave it in the container long enough, we all know what's going to happen. If the beaker is open, what will happen is that all the liquid will evaporate out from the beaker, and therefore eventually you'll have no liquid left, right? And that's because the molecules will be converted to the vapor and will escape into the atmosphere. So that's what happens in an open system like this. Now, if you have a closed system, as you can see here, you won't have the escape of the vapor molecules into the atmosphere. So the molecules here will go back to the liquid state, but at the same time, you have some liquid molecules going into the vapor state. So you have the back and forth taking place until equilibrium is established. And therefore, you're going to have at that point a fixed concentration of the gas above the liquid in this closed system. All right. Okay, so let's talk about the measurement of vapor pressure at 20 degrees Celsius and 30 degrees Celsius. And basically what we'll be looking at here is how the vapor pressure of a liquid varies with temperature. And you're going to see some very interesting patterns emerging when we look at the relationship between vapor and temperature. All right. Now, first thing I want to mention here is that the vapor pressure is not dependent on the amount of liquid or vapor present. So the point here is that it doesn't matter the amount of liquid that you start off with, and it doesn't really matter the amount of vapor that you start off with. The vapor pressure is independent of those two things. In fact, I would say the only thing that the vapor pressure is dependent on is, in terms of external factors, would be temperature. So, as stated here, it increases with temperature. When you increase the temperature of a liquid, then the vapor pressure increases. And that makes sense if you understand what's happening here. When you increase the temperature of the liquid, the molecules of the liquid will have more energy to escape into the atmosphere, and therefore, in a closed system, the vapor pressure would increase because more molecules will be moving into the gaseous state. So that's the relationship between the vapor pressure and the temperature. And we're going to see a graphical demonstration of that relationship shortly. But before we do that, let's look at how we can actually measure the vapor pressure of a liquid. So the apparatus that you see here is a setup that is used to do that. Now, let me just describe what's happening here. You have this flask here, which is called a filter flask. It's a thick-walled flask, right? So it's not a thin-walled flask. And it's connected to a manometer right here. I don't think I introduced this instrument to you, but basically it's an instrument that is used to measure the pressure of a gas that is in a container, such as the gas that will be present in this flask right here. It consists of a U-shaped tube, which has mercury in it, all right? Now, this flask here is stoppered with two holes. One hole has this pipe here, or this tube, I should say, which leads to a vacuum. So basically, it sucks all the air out of this flask right here. So therefore, there's no air inside here, all right? The same is true for this open, or I should say this region here above the mercury level here. There's a vacuum here as well, all right? So there's a vacuum as far as the flask is concerned, and there's a vacuum right here. Okay, the other hole has this particular piece of glass here, which has a stem pushed through it. It's called a separator funnel, and it has a liquid here. So I'm assuming that the liquid is water in this case, all right? So basically, this is a setup, and what we're going to do is, okay, well, this statement here is basically saying that the pressure here acting on the surface of the mercury here and here would be the same, which is actually zero before we do anything else, all right? So that means that there's no pressure exerted by anything inside here because this is totally evacuated. Okay, the temperature is 20 degrees. And then what was done was that the stopcock here was opened up and water is allowed to go into the flask. Now we all know what's going to happen. Eventually you're going to have vapor, water vapor above the surface of the liquid water. And that's because the water begins to evaporate. So you're going to have water molecules moving from the liquid state to the gaseous state. And that will continue until you have equilibrium between the liquid state and the vapor state of water. Because you have a vapor up here in the surface here, it starts to exert a pressure on the mercury level right here. And therefore, this mercury level will be pushed up because there's no pressure exerted here. So basically, there's a difference in the mercury level on the two sides of the U-shaped tube that you see here. And that difference is a reflection of the pressure that is exerted by the vapor, which is produced by the water in this system right here. So we can basically measure the height difference between the two mercury levels, and that will give us the pressure of the water vapor. So as stated here, the pressure exerted by the water vapor at 20 degrees Celsius is obtained by measuring the height difference here, which would be 17.5 millimeters mercury, which is basically the same thing as 17.5 torr, all right? So therefore, we can safely say that at 20 degrees Celsius, the vapor pressure of water is equal to 17.5 torr, all right? Okay, so that's what happens at 20 degrees. So the next question is, what happens at 30 degrees? What happens when you increase the temperature of the water? Well, as you can imagine, what's going to happen is that you're going to have more of the liquid molecules or the molecules in the liquid state. You're going to have more of them moving into the vapor state and therefore increase the vapor pressure above the water here. And that vapor pressure will be again exerted on the surface of the mercury here. And therefore that would result in a greater difference between the two mercury levels on both sides of the U-shaped tube. So as you can see here, that height difference has increased to 31 millimeters mercury, which is the same thing as 31.8 torr, all right? So at 30 degrees, right, the temperature would have increased. Well, the temperature was increased to 30 degrees and the resulting vapor pressure would have increased to 31.8 torr. And this is basically a pattern that is observed for all liquids. When you increase the temperature of the liquid, the result will also be the increase in the vapor pressure exerted by the liquid, all right? So that's basically what happens. And there are tables that have been put together showing the relationship between the temperature of a liquid and the vapor pressure. And this table that you see here is a table showing you the different temperatures for three substances: water, ethyl alcohol, and ethyl ether, and their corresponding vapor pressures measured in torr. And in each case, without exception, in each case, what you'll find is that as you increase the temperature, the vapor pressure increases. For water, you see that here. For ethyl alcohol, you see that here. And the same trend is observed when it comes to ethyl ether, all right? So that's a relationship between the vapor pressure of a liquid and the temperature of the liquid. As the temperature increases, the vapor pressure increases, right? So that's what you observe. Now, we can make comparisons between different liquids at the same temperature and see which one would have a higher vapor pressure. And if you look at the table here and the numbers associated with the different liquids here, you'll see that of these substances, the one with the highest vapor pressure would be ethyl ether. And this is true at any temperature. So that's what it says here. The vapor pressure at any temperature changes, or the trend is that ethyl ether will have the highest vapor pressure, followed by ethyl alcohol, and then water would be the last one in terms of the vapor pressure exerted. So it doesn't matter what the temperature is. That's a trend that you'll observe for the different substances. And that trend also correlates with the rate of evaporation. Basically, the substance with the higher or highest vapor pressure is the one that will exhibit a higher rate of evaporation. So the same trend that you see here, in the case of vapor pressure, you see basically the same trend for the three liquids in the case of rate of evaporation, all right? As I said before, this is true at any temperature. So if you choose 30 degrees, you'll see that water has the lowest vapor pressure at that temperature, followed by ethyl alcohol, followed by ethyl ether. And there are reasons for this, which I won't go into right now. I think we'll get into some of it later on in a later chapter. Okay, so that's showing you how the vapor pressure varies with temperature for different substances. So as stated here, the rate of evaporation of a liquid is proportional to the vapor pressure of that liquid. Okay, let's talk about this term, volatility, which relates to vapor pressure that we just discussed. Basically, substances that evaporate readily are said to be volatile. So as you can see, this term is basically a relative term, right? So we can compare two liquids and say which one is volatile, or which one is more volatile based on the vapor pressure that the liquid will exert. So just for comparison's sake, let's compare ethyl ether to water to mercury, right? And these are the vapor pressures of these liquids at a particular temperature, if I'm not mistaken, 30 degrees. So as you can see here, of these three substances, the one with the highest vapor pressure is ethyl ether. Its value is 442.2 torr. So that is considered for most intents and purposes to be volatile. Water, on the other hand, has a vapor pressure of 17.5 torr. So it is not as volatile as in the case of ethyl ether. So we say that water is moderately volatile. And then to the other extreme, we have mercury. Now, mercury is a liquid, which is also a metal. And you'll notice that the vapor pressure exerted by mercury is very low compared to water, and of course, compared to ethyl ether, 0.0012 torr. So for most intents and purposes, we consider mercury to be a non-volatile liquid, right? Because its vapor pressure is basically almost zero, all right? So that's basically what the term volatile means. It's referring to the ease with which a liquid will evaporate and produce vapors. Another term I want to talk about here, which is related to the intermolecular forces between molecules in a liquid, is this concept called surface tension, which is the resistance of a liquid to an increase in its surface area. Now, that is related to the attraction between molecules, especially the attraction of the molecules below the surface of a liquid to the molecules at the surface of a liquid. So as stated here, the surface tension is the result of the molecules at the surface of a liquid being pulled inward by the molecules that lie below the surface layer, right? So basically what we're talking about here is that the particles that are below the surface will have an attraction for the molecules on the surface. And that's the reason why if you were to, let's say, take a pipette, suck up some liquid, and then you push it out into, let's say, a beaker, dropwise, you see that the drops will take the shape of a sphere, or almost a sphere, all right, something kind of oval or spherical. And the reason why that happens is because basically the inner molecules will be pulling the molecules on the surface towards the center. So therefore, the result of that is that the droplets will have a more spherical appearance. All right, so that's the consequence of surface tension. Now, what you'll find is that substances which has large attractions between molecules will have high surface tensions. And a good example of that is water. All right, water, the molecules have a relatively strong attraction between each other. It's called hydrogen bonding, which we will talk about later on. But substances like water, which has very high attraction between the molecules, they will have a high surface tension. All right. Another consequence of molecular attraction or attraction between molecules is what is known as capillary action. Now, what is capillary action? Capillary action is a spontaneous rising of a liquid in a narrow tube, right? So if you have a very small tube called a capillary tube, and if you're involved in the health sciences, then you may come across these tubes when you're taking very small blood samples, for example, where basically you take the tube, an open end of the tube, and you dip it in the blood that you may obtain from a patient. Then you'll have the blood running up into the tube, right? Now, the reason why that happens is because of the strong attraction between the molecules of the liquid and the walls of the capillary tube, which is usually made of glass, right? So there are two types of forces at work when it comes to this sort of action. You have what are known as the cohesive forces, which would be the forces that exist between the liquid molecules. And then you have the adhesive forces, which would be the forces that exist between the liquid molecules and the wall of the capillary tube, right? Now, if the adhesive forces between the liquid and the walls of its container exceed the cohesive forces between the molecules, then the liquid will simply climb or move up the walls of the tube, all right? So that's the reason why water, for example, would move up a capillary tube, because the attraction between the water molecules and the glass material of the capillary tube would be stronger compared to the attractive forces between the water molecules themselves. Okay, so that's basically what capillary action is all about. Now, another manifestation of the interplay between the adhesive and cohesive forces is the shape of the meniscus of a liquid when it's in a glass cylinder, So water is a good example of this. If you put water in a cylinder and you look at the surface of the liquid water, then you're going to see a curve, right? A kind of lens-like looking curve, which is called the meniscus, right? And that would be the shape of the meniscus. It will have a concave shape. And this is also the result of the attraction of the water molecules to the surface of the tube, or in this case, a cylinder, all right? So this is a shape that's adopted because the adhesive forces between the water molecules and the glass will be greater than the cohesive forces that exist between the water molecules. So therefore, as a result of the adhesive forces being stronger, this would be the shape of the meniscus when you pour water into a graduated cylinder, for example, all right? Now, I will say this, that for other liquids, and the only example I can think of where the opposite is true is mercury. In the case of mercury, the shape, let me see if I have that diagram. I don't have it here. But in the case of mercury, let me try to draw it here. In the case of mercury, the meniscus is going to look something like this. It's going to be the opposite, right? And the reason why that happens is that the cohesive forces between the mercury atoms in mercury would be stronger compared to the adhesive forces between the mercury and the glass of the cylinder, all right? So basically the opposite is happening when it comes to the size or which one is greater, the cohesive forces or the attractive adhesive forces between the liquid and the glass. So just to recap this particular section right here, in the case of a liquid like water, the shape would look like what we had here before. Let me go back to my pointer. Oops. So the shape would... M1 Pro. the shape would look something like this in the case of water, because the adhesive forces would be stronger than the cohesive forces. But in the case of a liquid like mercury, the shape would look like this, and that's because the opposite is true. In other words, the cohesive forces will be greater than the adhesive forces. Okay. Another thing I want to talk about here is what is known as the boiling point of a liquid. Now, one might think that the boiling point, and I've heard students say this, that the definition of a boiling point is the temperature at which a liquid boils. Now, that's not the definition of a boiling point of a liquid. Here's a definition of the boiling point of a liquid. The boiling point is the temperature at which the vapor pressure of the liquid is equal to the external pressure above the liquid. All right. So what is implied in this definition here is that the boiling point is actually dependent on the external pressure, right? The next definition I want to give you here is what is called the normal boiling point, right? And the normal boiling point is basically the temperature at which the vapor pressure will be equal to the atmospheric pressure, where the atmospheric pressure is 1 atmosphere, all right? So that's what's called a normal boiling point. Okay, so with those definitions out of the way, I want to show you again this table which we looked at earlier, which shows you the relationship between the temperature and the vapor pressure of the different liquids, right? So if we look at in the case of water, right, you'll see that at 100 degrees Celsius, the vapor pressure of water is 760 torr, which is equal to 1 atmosphere, all right? So basically what that means is that the 100 degrees here would be the normal boiling point of water, because at that temperature, the vapor pressure of water is equal to the atmospheric pressure, which is 760 torr, all right? So that's basically how we determine the boiling point of any liquid. In fact, the next slide, well, not this slide. Well, let me just say something about this slide first, and then I'll show you the graph which shows you the relationship between vapor pressure and temperature. So this graph, this table, I'm sorry, basically lists different substances, their boiling points, their melting points, which we'll talk about shortly, the heat of vaporization, which we will be using shortly, and the heat of fusion, all right? So as you can see here, water has a boiling point of 100 degrees, and other liquids will have different boiling points. So these are the temperatures at which the vapor pressure of these liquids would be equal to 1 atmosphere. Okay, so as stated here, the boiling points for different substances can be plotted on a vapor pressure versus temperature curve, which is what I'm going to show you right here. So this is a plot of vapor pressure on the y-axis and the temperature in Celsius on the x-axis, all right? And these are the different plots for these liquids. You have ethyl ether, you have ethyl alcohol, and the blue curve is for water, all right? So if we look at the vapor pressure of the liquid being equal to 1 atmosphere, which is 760 torr, which is represented by this line right here, then all we have to do to find the boiling point of each of these liquids is drop a horizontal line, or I should say a vertical line, at the point where this horizontal line cuts each curve. So for example, in the case of ethyl alcohol, this line, when it hits this curve right here, you drop a vertical line, and where it cuts the x-axis, that would represent the boiling point, the normal boiling point of ethyl alcohol, which turns out to be 34.6 degrees Celsius. If you do the same thing in the case of ethyl alcohol, the boiling point is 78.4 degrees Celsius. And if you do the same thing for water, as we said before, the boiling point is 100 degrees Celsius, all right? So that's basically how you can determine, based on these curves, that's basically how you can determine the boiling point of the liquids, the different liquids at 760 torr. In fact, you can use this curve or these curves to determine the boiling point at pretty much any pressure, any vapor pressure. So as stated here, the boiling point at any temperature can be found. Or I should say any pressure can be found. So for example, if you look at this here, same curves, and let's say you want to find the boiling point of ethyl alcohol at 500 torr. Then what you do is draw a line from 500 here, which is on the y-axis, and where it touches the curve for ethyl alcohol, you drop a vertical line down, and where it cuts the y-axis, where it cuts the x-axis, would represent the boiling point of ethyl alcohol at this pressure of 500 torr, which turns out to be 68 degrees Celsius. All right. So that's basically how you can determine the boiling point of a liquid using this curve, the vapor pressure versus temperature curve, at pretty much any pressure. All right. Once you have the pressure value here, you can determine the corresponding boiling point. So this is showing you the same thing. This time when the vapor pressure is 700 millimeters mercury, the corresponding boiling point would be about 77 degrees. So basically, as the vapor pressure, as the external pressure increases, the boiling point increases. All right. So that's why I said earlier, I don't know if you caught on to it, but I said that, basically the boiling point is dependent on the prevailing pressure that is exerted on the surface of the liquid. Okay. So much for boiling point. So let's talk about what we call a freezing point, which is the same thing as a melting point. So freezing point, melting point, both one and the same. So this has to do with a situation where you have a liquid that is converting to a solid. So you have a change of state. And that process is called freezing or solidifying, right? But if you're doing the reverse, if the solid is changing into a liquid, then that is said to be melting. And both processes will occur at the same temperature, all right? So that's the reason why the melting point and the boiling point are considered to be one and the same, all right? So here is a definition of the boiling point or melting point, and that is the temperature at which the solid phase of the substance is in equilibrium with its liquid phase. That basically is what the boiling point, not the boiling point, the melting point is, or the freezing point, all right? So basically it's a temperature where you have this equilibrium taking place between the solid state and the liquid state. So you're gonna have the back and forth between those two, all right? And just to illustrate this, so the little blocks here represents the solid state of water that is present in the liquid state, which is represented by everything else here, the blue substance here. So basically at the freezing point, which in the case of water is 0 degrees Celsius, and if the pressure is 1 atmosphere, as soon as a water molecule goes into the liquid state, another water molecule goes into the solid state, right? So basically you have that back and forth taking place, where as soon as a molecule goes into the liquid state, another molecule goes into the solid state, all right? So that's why this situation is basically a dynamic one at equilibrium. Okay, so we talked about the boiling point, and we talked about the melting point, which is the same thing as a freezing point. So now we're going to talk about changes of state. What happens when you go from one state to another? So you could go, for example, from the liquid to the gaseous state, and then from the gaseous state, or you can go from the liquid state to the solid state. So it all depends on, the type of question you're given when it comes to problem solving. Okay, so what you're looking at here in this diagram is what is called a heating curve. And this is a plot of the temperature, which is on the y-axis here, versus the amount of heat added, right? So we're starting with a substance, in this case, ice, and this could apply to pretty much all other substances. In the case of ice, we're starting with it from below the freezing point. The freezing point of water is 0 degrees, right? So we start heating the ice, and of course, we know what will happen. The temperature will start to rise until you get to the freezing point of ice. 1 minute, please. Okay, so when you get to the freezing point of ice, what happens is that you're going to have the conversion of the solid ice to the liquid water, right? But the freezing point, or the temperature, will remain at the freezing point as long as you have that process taking place where the ice is converted to liquid water, all right? So that continues from point B to point C. So at point C, what happens is that all the ice is converted to water. Now, if you add more heat, what's going to happen, of course, is that the temperature of the water will rise. And that will continue until you get to the boiling point of water, which is represented by point B. And then as you continue heating, what happens is that the liquid water will be converted to water vapor. That process will continue, but at the same time, the temperature will remain at 100 degrees. As long as you have liquid water there, the temperature is going to remain at 100 degrees while the water is converted to the water vapor. When all the water is converted to the water vapor, then what will happen is that you have only steam, and the temperature of the steam will rise as you continue to increase the temperature of the steam. So that's basically an overview of the process of converting from solid ice to water, liquid water, and then from liquid water to water vapor. All right. And basically it shows you how the temperature varies as you go through each step. Okay. So that's basically the heating curve that's associated with, in this case, water. And this is true pretty much for all substances, right? They go through the different changes. The only differences would be the melting point values and the boiling point values. But apart from that, pretty much all substances go through this process. Okay, now at this juncture, I want to introduce to you another term, which is called the heat of fusion. And that term was actually listed in a table I showed you earlier. Let me go back to the table here. Well, let me give you the definition first. I'm sorry. So the definition of heat of fusion is given right here. The energy required to change 1 gram of a solid at its melting point into a liquid, right? So that is the definition of the heat of fusion. The energy required to change 1 gram of a solid at its melting point into a liquid. And there, the table I showed you earlier gives you the value of the heat of fusion. Let me go back to it here. Okay, this table right here. So in the case of, well, there are 4 different substances here, right? So the heat of fusion is given here for 2 of those substances, for water and ethyl alcohol. So as you can see here, the heat of fusion here is given as being equal to 335 joules per gram, which is the same thing as 80 calories per gram, all right? So as you can see here, the units that you're going to use for heat of fusion is dependent on whether or not you're going to use the metric unit of joule or the non-metric unit of calories, all right? So that's the heat of fusion. And I need to write this down because we're going to need this to solve a particular problem. Let me write this down on this paper right here. So heat of fusion of water is equal to 335 joules per gram. Okay, so let me fast forward to where we left off earlier. Okay, so here is an example based on what we have just talked about. The question is asking how many joules of energy are needed to change, move this out of the way, 10 grams of ice at 0 degrees Celsius to water at 20.0 degrees Celsius. Okay, now in order for us to do this problem, we have to look at this particular process in parts. So let me go to my pen. All right, so you're going to start off with ice, which is H2O solid, at 0.00 degrees Celsius, all right? And you're going to heat it. Now, what's going to happen first is that the H2O solid will be converted to H2O liquid, all right? And the temperature is still going to be 0.00 degrees Celsius, because remember, we said that as you go from the solid state to the liquid state, the freezing point of the temperature of the liquid and the solid together will be the same until all the solid has been converted to liquid, all right? Once all the solid has been converted to liquid, then what's going to happen is that with continued heating, the liquid H2O has its temperature increase from 0.00 degrees Celsius to 20.0 degrees Celsius, all right? So this is basically a two-step process that we basically interpret this question as, so that it makes it easier for us to do the work in terms of calculating the amount of energy needed to carry out the entire process. Now, this is melting here, right? And the energy required for melting is what we call the heat of fusion, which is the heat energy required for melting 1 gram of a substance. And remember, we said that the heat of fusion, we saw it in the table earlier, is equal to 335 joules per gram, all right? So, how do we calculate the total amount of energy for both steps? Well, in the case of step 1, what I'm going to do is call the heat required here as being equal to Q1, and this would be Q2, all right? So how do we calculate Q1? Well, Q1 would be equal to the mass of the ice, which is 10.0 grams, times 335 joules per gram, all right? So the gram units will cancel out here, and you're going to end up with 3350 joules. So that would be the amount of heat needed to melt 10 grams of ice into water. Then for the second part, where you're heating the water from, the liquid water, I should say, from 0 degrees Celsius to 20 degrees Celsius, in order for you to do that, there's an equation that we used before in chapter, I think it was 10, right, chapter 10, and that is this equation, which should look familiar to you. M times C, I'm sorry, folks, let me do this again. Q2 is equal to M times C times delta T. That should look familiar to you, right? M is a mass of water, C is the specific heat of water, and delta T would be the change in temperature. So in this case, M would be 10.0 grams multiplied by C, which of course you can get from the document in Canvas, 4.18 joules per gram degrees Celsius times delta T, which would be the difference between 20.00 degrees Celsius minus 10.00 degrees Celsius. And that's basically the setup. So let me, where's my calculator? Okay, so, oh, this should be 0, by the way. I'm sorry. This should be 0, not 10. I don't know what I was thinking. This should be 0.00. Okay, so let me see here. 20 minus 0 gives you 20. So 20 times 4.18 times 10. And according to my calculations, this works out to be 836 joules. So therefore, Q total would be equal to 3350 joules plus the 836 joules that we just calculated. And whatever that gives, that would be the answer. So that plus 3350, according to my calculations, this would be equal to 41, we have to round off to 4190 because the highest decimal place, so to speak, is the 10th place. So this would be 4,190 joules. And that would be the answer for this particular question. Okay, any questions about this example? Any questions? Any questions? Okay, so moving along. Okay, another term. Hold on, let me see. Okay, another term that, what time is it? 4:46. Okay, another term that we need to learn about is what is called the heat of vaporization. And it's very simple, or I should say very similar to what we said about the heat of fusion. The only difference is that this is dealing with a situation where the liquid is being converted to a vapor at the boiling point. And that's what heat of vaporization is all about. The heat of vaporization is the energy required to change 1 gram of liquid at its boiling point into a vapor. All right. So that's the heat of vaporization. And we met that before in the same table. Let me go back to the same table. Sorry about that. But I need to show you this. Okay. So the heat of vaporization of water is right here. And let me write that down as well. 2259 joules per gram. All right. So this is the enthalpy of the heat of vaporization. All right. 2259 joules per gram. All right. Okay. So let me go back to where we left off. Okay. So based on what we have just talked about, we should be able to do this example. So this question is asking, how many kilojoules of energy are needed to change 20.0 grams of water at 20 degrees Celsius to steam at 100 degrees Celsius? So again, we have to break this down into different parts. So you're going to have H2O liquid at 20.0 degrees Celsius converted to H2O liquid at 100.0 degrees Celsius. And then we have H2O liquid converted to H2O gas, again at 100 degrees Celsius. All right. So again, we need to calculate Q1 and Q2. All right. So Q1, again, because it's the liquid being converted, well, not converted, but the temperature has changed from 20 degrees Celsius to 100 degrees Celsius. We're going to use Q1 is equal to M times C times delta T, which is equal to M, which is 20.0 grams, times 4.18 joules per gram degree Celsius, times the change in temperature, which would be the difference between 100.0 degrees Celsius minus 20.0 degrees Celsius. All right. So that's basically how you calculate Q1 right here. Now Q2, because we're talking about vaporization in the case of Q2, then that would be equal to the mass of water, which is again 20.0 grams, times the heat of vaporization, which is 2259 joules per gram. And that's how you work that out. So I should have worked this one out first. So for the first one, for Q1, that's 100 minus 20, which gives you 80 times 4.18 times 20.0. And according to my calculations, this works out to be equal to 6688 joules. And then in the case of Q2, that would be 20 times 2259. And rounded off to 3 sig figs, this would be 45200 joules. All right. And if I were to convert, well, to get the total Q2 or QT, which is the total heat change, that's going to be 45200 joules plus 6688 joules. Let me work that out. That's 45200 plus 6688. So according to my calculation, this works out to be equal to 51900 joules. And we have to convert this to kilojoules because the question is asking for the answer in kilojoules. So we have to multiply by this conversion factor where we have 1 kilojoule above and 1,000 joules below. And that works out to be equal to 51.9 kilojoules. So this would be the final answer to this question. Okay, any questions about this particular example? Any questions? Any questions? Okay, so what shall we talk about next? Okay, so let's talk about a special type of intermolecular force known as the hydrogen bond, a very important phenomenon because, believe it or not, our very lives are dependent on this particular feature. Now, if you look at the hydrogen compounds of group 6, which are listed over here, you have H2O, H2S, H2SE, and H2TE, right? One striking feature that you realize, which is the difference between the water and all the others, is that water has a very high boiling point compared to the other substances. So as you can see here, water has a high boiling point of 100 degrees Celsius, and then hydrogen sulfide has a boiling point of minus 60.3, and H2SE has a boiling point of minus 41.3, and H2TE has a higher boiling point or a low boiling point of minus 2. So these here are very low, obviously, compared to that of water. Another thing you'll notice is that the heat of fusion and the heat of vaporization of water is significantly higher compared to the other substances. So if you look at the heat of fusion here, for water, it is 335, as we said before. But when you compare that to hydrogen sulfide, you see that hydrogen sulfide is 69.9. And in the case of hydrogen selenide, it's 31, all right, joules per gram. And you see a similar trend in the case of the heat of vaporization of water compared to the others. As you can see here, the heat of vaporization of water is 2.26 times 10 to the 3 joules per gram. And then you see the next in line is 548 in the case of H2SE, 238 in the case of H2SE, and 179 in the case of H2TE, all right? So as stated here, the melting point, boiling point, heat of fusion, and heat of vaporization of water are extremely high and do not fit the trend of properties that you see for these compounds, which are the hydrogen compounds of group 6 elements. Even though water has the lowest molar mass, all right? So how do we explain that? Well, let me just skip all this here. Oh, I forgot to mention here, the melting point also for water is high compared to the other substances. So water has a high melting point, even though it's 0, but when you compare that to H2S, it's minus 85.5 for hydrogen sulfide, minus 65.7 for H2SE, and minus 49 for H2TE. So even the melting point is higher compared to the other substances for these elements or the hydrogen compounds of these elements. All right, so let me just skip here and talk about the reason why water exhibit these unusual properties. And that is because of a particular phenomenon known as hydrogen bonding that exists between the water molecules, right? Now, the term hydrogen bond is a bit of a misnomer because it's not a bond in the sense of a bond between two atoms in a compound. It's actually what we call an intermolecular force. It's a force that exists between atoms of different molecules, all right? And what you'll find is that in the case of hydrogen bonding, it is formed between polar molecules that contain hydrogen covalently bonded to either fluorine, oxygen, or nitrogen. And if you are sharp enough or aware enough, you realize that fluorine, oxygen, and nitrogen are the 3 most electronegative elements that exist. So therefore, any compound which contains hydrogen bonded to any one of these 3 elements, then those compounds will display hydrogen bonding, all right? So that is true, for example, in the case of hydrogen fluoride, right? Hydrogen fluoride will exhibit that type of intermolecular interaction, which is known as hydrogen bonding. Anything also that contains an oxygen to hydrogen bond will exhibit that feature. and anything that contains a nitrogen to hydrogen bond will also display that particular phenomenon. All right. So how does this work? Well, when hydrogen is bonded to any one of these three electronegative atoms, then what happens is that you're going to have a very strong displacement. Let me just do a little diagram here. In fact, let me get out of this here. And let me go to my sketch pad here. Oh, actually, there's a diagram here. Okay, let me go back to the PowerPoint. So let me, okay, so we're going to use hydrogen fluoride as an example. So in this particular case, what happens is that because fluorine is bonded to hydrogen and the fluorine is more electronegative than hydrogen, what happens is you're going to have a very strong pull of the shared electrons between the two atoms towards the fluorine. So these electrons here, which represents the bond between hydrogen and fluorine, will be pulled to the fluorine atom. So as a result, this has a partial negative charge. Now, in the case of hydrogen, this has a partial plus charge. And this plus charge is going to be relatively high because hydrogen is such a small atom, which has only one electron is sharing with the fluorine. So therefore, that one electron is being pulled away from the hydrogen to the fluorine. So this hydrogen here has what we call a high charge density. And because it has a high charge density, there will be a strong attraction between the negatively charged fluorine of another atom towards the hydrogen of this molecule, right? So basically, the strong attraction is what we call the hydrogen bond, all right? So it's very important that you understand the difference between the normal covalent bond and the hydrogen bond that exists between the hydrogen from one atom and in this case, the fluorine from another atom. That association is what we call the hydrogen bond, all right? So the hydrogen bond is a very important feature because, especially when it comes to the properties of water, it is because of this strong intermolecular force that exists between water molecules that results in water having a high boiling point, a relatively high freezing point, a relatively speaking high heat of vaporization, and high heat of fusion. And also the specific heat is also relatively high because of the hydrogen bonding. Hydrogen bonding is also responsible for the high surface tension that exists on the surface of a water molecule, all right? And going back to what I said earlier about the boiling point being high for water because of hydrogen bonding, that's very important because if it wasn't for hydrogen bonding, then the boiling point of water would be low, and therefore that could affect life on Earth, for example. There would be no rain, there would be no rivers, there will be no seas because water will not exist as a liquid if there was not hydrogen bonding between the water molecules, all right? So hydrogen bonding is very important. Even our very lives are dependent on it. Okay, so this is showing you the hydrogen bonding that exists between water molecules, all right? So basically the red spheres here, let me get back to my pointer. Basically the red spheres represents the oxygen atom, and the blue spheres here represents the hydrogen atom. And basically what happens is the oxygen, let me go back to my pen here. So I'm going to draw hydrogen here, bonded to oxygen, bonded to hydrogen, right? So again, oxygen is more electronegative than the hydrogen. So therefore this pair of electrons, for example, here will be pulled towards the oxygen. So as a result, the oxygen will have a partial negative charge, and the hydrogen will have a partial plus charge. So that means another water molecule can come close to the first water molecule, and this negatively charged oxygen will attract the positively charged hydrogen. So that interaction right here is the hydrogen bond that exists between the hydrogen of one atom and the oxygen of another atom. I'm sorry, the hydrogen of one water molecule and the oxygen of another water molecule. So that is what is being shown here. This is the oxygen. This is the hydrogen from another molecule. So that would be the hydrogen bond that exists between those two molecules, all right? So basically, if you could actually see the water molecules in a sample of water, as stated here, it will exist as aggregates in which the water molecules are linked to each other by hydrogen bonding, all right? So that's basically what happens in the case of water. And something similar will happen in the case of other molecules, which contains hydrogen bonded to either oxygen, nitrogen, or fluorine, all right? Okay, so that's basically the end of this chapter. So that means that, let me go to Canvas, whoops, wrong one, let me go to the Canvas here. So that means that you should be able to do, let me see here. Let me see here, chapter 14. Okay, there's only one assignment for chapter 14. Let me keep this one. Let me unpublish this one. Let me do a quick look over of this particular assignment here. Just to make sure everything is in the right place. Let me see here. Let me open this up. Okay, so let me see, number one is that. Number two is that. Let me see here. Okay. Okay, I think, you know what? I think, let me check something out here because I think you won't be able to do number 5. So let me check this other assignment here because I remember there were some issues with this particular assignment when I gave it earlier. I think I may need to make some changes. Okay, you know what? I realized something. Okay, let me change. Let me get rid of, let me unpublish this and publish this version. This is the one that you should be able to work. Let me just check it one more time just to be sure. Let me see. Okay. Okay. So this is it. So you should be able to do that assignment. So let me make sure that the folder itself would be visible to you, chapter 14 folder. I'm going to publish it now. So now you should be able to access it, right? So you should be able to do that assignment. Also, let me talk about your upcoming tests. So I'm still, believe it or not, grading some of your assignments that some of you have turned in. The main reason why it's taking so long is because some of you have turned in your stuff late. But I plan to post the assignment keys later on this evening. And somewhere between this evening and tomorrow morning, I will be emailing you guys the your graded assignments so that you can have that to review as well, right? So between tonight and tomorrow morning, I will be sending you your graded work. Of course, if you have any questions or any concerns about anything I've graded, please feel free to contact me concerning that. And your test will be next week, and it's the same arrangement as what we did the last time. I'll be posting a test on Canvas on Monday, and you have until Friday of that week to complete it. All right. And of course, you should scan it as a PDF document and upload it into Canvas. Of course, I'll provide the portal for you to upload your tests. All right. And again, let me remind you that the test will be based on chapters. 1 minute here. Test number 2 will be based on. Okay, I don't have the chapter numbers here, but I do have the assignment numbers, which is assignment 8. Let me check something here. Oh, if I remember correctly, it's from chapter 5. Let me just check here. Right, chapter 5 to chapter 8. Let me check here. Chapter 5. Right, so chapter 5 to chapter 8. The corresponding assignments will be assignments 8 through 17. All right. So that's basically what your test is based on. Any questions? Any questions? Any questions? I'm thinking that for the next class, we can do a bit of a revision for your test. So if you have any questions, any area of difficulty that you may have, feel free to come with your questions. So I'll just spend some time reviewing, whatever problems you might have concerning any of those 4 chapters. All right. So next class will not be like a lecture, just, review. All right. So if there are no questions for today, that's pretty much it. So I'll see you guys on Wednesday. All right. So take care and enjoy the rest of your day.